Charlie Macklin here. This evening I'd like to do a video about the sun. This is my model of the sun. It's not the greatest in the world, but it looks pretty cool. A little lumpy. A little lumpy. The first part of the video, we're just going to go over some basic sun facts. And then I will get to my hypothesis on how the sun actually works on the interior. Sun facts. The sun is a sphere. The sun rotates once every 25 days. It's about 73.5% hydrogen, about 25% helium, and 1.5% trace other materials like oxygen, iron, and other things. The sun is about 864,000 miles wide, almost 1,000,000 miles across. One side to the other. It's a big boy. It's 93 million miles from Earth, and that means it takes 8 minutes for the light to get here. I'm trying to hide the reveal for you as this meatball floats around in my garage. The sun actually produces a vibrational sound. 126 hertz. It produces a sound frequency. I find this to be very interesting because the Earth produces a frequency around, I think 6 or 8 hertz, about 8 hertz, the Schumann resonance. The sun produces a sound 126 hertz. That's right around a B2 on the old piano there. The 27th key from the left on the piano, if you're into sound and music and stuff. And the temperature ranges from the very center. It's been measured to be the hottest at I want to say 27 million degrees Fahrenheit. It's about 15 million Kelvin, and most of your measurements are in Kelvin on these astronomical things. So 15 million Kelvin, and then there's a zone in the center, the radiation zone, the radiative zone, where it ranges from 7 million down to 2 million. And then there's a very relatively cool layer at 5,800 Kelvin, which is about 10,000 Fahrenheit. And then it warms back up in the convection zone on out to the corona, the coronal ring around the, or not ring, but the corona sphere around the sun. And it's up to 1,000,000 degrees again. So there's definitely some odd things going on if you're just looking at that data. Well, here's my theory on how it all works. Dun, the inside of the sun. It's, in a sense, hollow, but not any kind of hollow you would know about. Let me explain my hypothesis. So this is the outer shell, and this is the inner zone, right? In this outer layer, which is normally called the convective zone, you have mostly hydrogen and some helium interacting with some, perhaps some nuclear combustion, but they're interacting as actual atoms in this layer, okay? In my hypothesis, there's a boundary layer, and I call it the singularity horizon. And if you cross that horizon, you go into the radiative zone. Matter cannot exist in any atomic form. In other words, it has to shred into either protons, neutrons, or electrons. And when it does that, it then assimilates or joins to the organized central core. And the very center is a proton core that would be about, I estimate about half a mile wide, of solid protons. And it would weigh an extremely heavy amount. Very, very heavy. It would weigh enough to power the entire solar system. Very, very dense material. And I believe it's spinning at about 126 times per second. That's what causes the sun to produce its audible sound, while the outside rotates at a slower speed. The inner core is spinning like a little motor in there. And it's either that or the shell's vibrating. There's got to be a reason why it vibrates at such a high frequency, even though it's such a large mass. Okay? So in this central zone, there's an electron cloud that's hundreds of thousands of miles across. Of course, this model's not to scale. I couldn't build it to scale. But the central core, I believe it's about half a mile wide. It might be a quarter mile, it might be 1 mile. But it's a small, relatively small chunk of protons. But there's trillions of protons in there, just densely packed together. And then a massive electron cloud outside of it. Essentially, the whole sun is just one giant atom. And I know you're probably, if you're into chemistry, you're going to say, well, that can't be. You get an atomic number up around 100, and it falls apart. How can you have trillions of protons in there? And my answer to that question would be, well, the same reason you can have a neutron star, gravity. If you get enough gravity, it'll overpower the microscopic phenomenon you see, and you reach a critical mass where you can have a proton core. And so individual hydrogen and helium atoms just simply cannot exist in this area. They will be shredded into their subatomic components and join the nuclear reaction in the center. So you can think of the sun as an atom that has an ever-increasing atomic mass. Now, there's a limit to it because obviously there's a fuel shell around the outside. And you would say, well, this layer is plasma. That's what Wikipedia says. Well, it's plasma. It's just protons and electrons. But that doesn't make sense to me. The protons are heavier. They would gravitate towards the core and form some sort of a densely packed rotating core with an electron cloud outside of it. So as these fuels here work their way in, they would break apart into subatomic particles and then have to work their way through this massive high temperature electron cloud, which in a way is hollow, but it's under very high pressure. You can think of it like an electrical force field, and it's at a very high temperature. And then any particles that were left, like protons, would join the core. If it was a neutron, it would break and change and do what it has to do and release energy and join the core. On the outside, where you have coronal discharges and stuff, the reason the corona can get up to temperatures, which you maybe can't see in this model, but temperatures that would get up to 1,000,000 degrees, while this layer is only 5,800 degrees, is because it's plasma, which means loosely contained, protons and electrons moving around, but there's not an organization to it. Once you cross the singularity boundary, there's an organization to the way the molecules go, and it has to join the one singularity that is the sun's core. You would see this same phenomenon in a neutron star. So in a neutron star, it might be 10 or 20 times larger. And eventually that type of star has what you call a supernova. And I would say that that's what you would call a gravity-controlled death. In other words, the proton core at the center of a supernova-type star gets bigger and bigger, and the gravity is so strong that the shell cannot hold itself in, and it collapses in on the electron cloud, forcing all the electrons into the protons, making neutrons, and releasing a tremendous amount of energy, and leaving a very dense chunk of neutrons, about 10 or 20 miles across, that rotates, and these are well identified in astrophysics as quasars and pulsars. So that's what happens if you have a star that's way bigger than ours. In our case, our star will suffer an electrical death, and what that means is, as the protons join the core and the electrons join the electron cloud, eventually it tries to jump to another valence level, the way an atom would. So this electron cloud swells and pushes the fuel out further, which cools the reaction in a way, but also makes the sun much larger in size. And when that happens, that's what's known as a red giant. And that's what our sun is predicted to do at its death. So it would have a an extinction based on electrical phenomenon rather than solely crushing in on itself with gravity. So that's my theory on, or hypothesis rather, on the sun. I hope I didn't go too fast or too slow. I'm trying to pump a lot of information out there. Anyway, I know I'll get some comments sooner or later. Somebody will say, well, you're wrong. But I'd love to see some data, and I think the model's pretty good. I think it'll show some truth in the future as people send more probes to the sun. You know, NASA's looking to do another one here, I think in a couple of weeks. Not into it, but, you know, fly near it with different testing equipment. So anyway, Neil deGrasse Tyson, let's have some tea, buddy. Let's do it. Y'all have a good evening.